Hi, everyone. Good afternoon. Today we have Gilles Louppe from the University of Liege in Belgium. He previously held some positions in CERN and also in NYU. And today he'll talk about the frontier of simulation-based inference. So Gilles, I'll leave the audience with you, please.
Okay. Well, good afternoon, everyone, and thanks, Cesar, for the invitation. So the talk I will give, so what I will talk about today is simulation-based inference. I will start with first describing where it is useful and then how you can use it. And then finally, I will conclude with a word of caution about current algorithms and things that maybe you should check if you are interested in using these methods. Okay, so if you look at science in general, it's really full of scientific simulators these days. So if you look at the smallest of the distance scales in fields like particle physics that simulate collider experiments, then all their theoretical model is expressed as computer program scientific simulator that you can run to produce the kind of output that you think you will observe in the real experiment. And this is true across many, many length scales. So from the tiniest distance scales to the largest, for example, up to the entire evolution of the universe in cosmology, where again, you have a computer program scientific simulator that you can use to simulate how the universe evolved from the Big Bang up to now and also in the future. Of course, you have other sciences like weather and climate that also make heavy use of scientific simulations, neurosciences also to simulate the behavior and the connectivity of neurons in brains, and many other fields like this. So what is common to all of these scientific fields is that the knowledge, the scientific knowledge, is not described just as a bunch of equations, but really everything is expressed as a computer program that really encapsulates everything that we think that we know about the process that we are studying. And this is very convenient because when you express things this way, a data generative process as a computer program, what you have is some kind of causal mechanistic description of the data generating process that you think is giving rise to the data that you observe. So that's why I think it's everywhere in all of the sciences. So to make things a bit more concrete and maybe a bit more formal, in my language, I will say that a scientific simulator can be abstracted as a probability distributions over three elements. So first, we would have theta, which correspond to the parameters of interest, so the quantities that we are interested in measuring, for example. Then we have, at the end of the simulation, we have observations, synthetic realizations of the data generating process that you simulate that I call X. So basically, these are the things that you think you will observe in your experiment or in nature. And then in the middle, you have Z, which correspond to latent variables. So all random choices, for example, that could lead starting from some parameterization theta to the observation X, okay? And so you can view that when you run a scientific simulator as something which generates random trajectories, as you see here on the slide. And as you simulate, eventually you will arrive at some point in some observation space that will produce some outputs, okay? So this is what we call the prediction when you run simply your simulator forward. However, what you are really interested in is to do the opposite. So you would start from actual observations that you get from your experiment, and then you would like to identify all those random trajectories that could have led to these particular observations that you want to condition on. Okay, so this is what we call inference, which basically involves solving some kind of inverse problem in which you would start from some observations, and then you would like to identify all the latent values Z's together with all the parameterizations theta that could have led to this observation. Unfortunately, when you take scientific simulator written expressed as computer program, doing this type of inference is very inconvenient. And one of the reasons is that the likelihood function, so P of x given theta, which ties basically the observations to the parameters of interest, should be expressed as the integral over all the random trajectories, pxz's, that could have started from theta. And this integral is intractable, meaning that we have no way to evaluate this quickly. And this is quite inconvenient because if you want to do inference, for example, if you want to do Bayesian inference, the key ingredient that you will need is the likelihood functions together with a prior, and then you will be able to derive a posterior. The same if you want to do a frequentist type of analysis, you will need at some point in your analysis to be able to evaluate the likelihood function. But here in this setup, we are in a setting where we cannot evaluate the likelihood function. Okay, so this is what we call the likelihood-free inference setup, because we don't, I mean, this likelihood function exists. We can sample from it by running the simulation forward, but we cannot evaluate the precise value, the precise density value of any final observation x for some parameterization theta. So given this constraint, what we want to do is to solve an inference problem. So formally, I would say that we start with a simulator or computer program that let you generate samples, so x values that you draw by running your simulator for some parameterization theta of the model parameters. Then you would assume that you have some actual observed data, let's call it x ops, and you would assume that in this case, your simulator is well specified, meaning that there is some configuration of the parameter theta true that could have produced this observation. Then if you are Bayesian, you would also assume that you have prior beliefs about the model parameters. And then what you would want to solve as an inference problem would be either to estimate, to produce a point estimate of theta true, starting from x naught, or to produce some confidence set that would basically correspond to all values that are plausible for all value of the parameters that could have plausibly generated the data. Or if you're a Bayesian, you would like to estimate the posterior distribution P of theta given x naught. Okay. So how do we do that, given that we cannot approximate the or just even evaluate the likelihood function? So to do that, we need new algorithms, or we need dedicated inference algorithms. So this is not a new problem in itself. This has been known in many different fields. I mean, all of the scientific fields that I've been talking about have been faced with this problem, and some of them came up with solutions. And so, for example, approximate Bayesian computation is one of these solutions which was proposed in the early 2000s by scientists in genetics and population biology. And histograms is another way that you can go around this problem, and which is the type of analysis, for example, which is used by physicists at CERN. What I will talk about today is how machine learning, recent developments in machine learning have been expanding this class of algorithm to be able to tackle problems for which the dimension of the data, the x, becomes very, very large, or when the cost of running the simulation increases. Because for some scientific field, it could be that generating synthetic data, thousands of random realizations just take maybe less than a minute. But for some other, like for example, cosmology, if you want to generate a full universe over a time horizon of several billions of years, it could take hours or even days just to produce one synthetic observation. Okay. And so there have been recent developments. Many algorithms have been proposed mainly by the machine learning community, like neural likelihood ratio estimation, the one, the algorithm I will talk about today, but also others like neural posterior estimation, neural likelihood estimation. All of these three algorithms, what they are trying to do is to learn part of the base rule, for example, directly trying to approximate the likelihood function, with a neural network, and then you plug this approximation, this surrogate into classical algorithm like MCMC, and you go on. Neural posterior estimation does more or less the same thing, but it tries to directly approximate the posterior distribution using variational inference. And what I will talk about, neural likelihood ratio estimation tries to estimate the likelihood to evidence ratio using binary classification. You also have sequential method. I will not talk about them today, but here the thing is that running the simulator is so costly that you want to make use of your computational budget as best as possible. And maybe you even want to dedicate this entire budget just to do inference on one specific observation. And this is what you can do with sequential methods. And finally, you have other methods like gold mining, which basically do not see the simulator as a black box any longer, but tries to capture quantities that are generated when you simulate forward, and then to make use of these quantities to improve the learning of all these machine learning models that you have there. Okay, and this way, basically, you would use more efficiently all the information which is generated during the simulation than just the final observation only, as it is the case for this family of algorithms. And so in our review paper, The Frontier of Simulation-Based Inference, we identify three different directions that lead to the improvement of these algorithms. The first one is really driven by recent progress in machine learning, which really expand the family of problems that you can address, but only in the direction mainly of the dimension of the data. Then the progress in active learning is driving the expansions toward more and more costly simulations. And then you have this kind of intermediate thing in between, which we call augmentation integration, which tries to make use of what's inside the simulator to expand the family of problems that we can address across both directions at the same time. Okay, so today I will talk about first ABC, approximate Bayesian computation, and then neural likelihood ratio estimation. Okay, but there, of course, there are plenty of other algorithms. This is just to show you two of them and to tell you how they work and what you can do already with them. So approximate Bayesian computation is maybe something that you've known about. The idea is quite simple. You have a simulator which you treat as a black box. Then you have parameters, so you can decide what are the values that you put as input to your simulation. And then you just run your simulator forward, and that generates observations, random observables X. Okay. And what you do is that if you want to do Bayesian posterior inference, so to approximate P of theta given X naught, what you do is that you compare all the synthetic observations that you generate to your actual observation. Okay, and the way you do that happens in two ways. First, you compress the data through a summary statistic. So you change the representation of the data from X to X prime. For example, you would compute summary statistics. I don't know, like if you generate images, like a kind of statistic that you could be interested in using is, for example, an histogram of the, I don't know, the color intensities in the pixels. And then you do the same, you also compress in the same way your observation X naught. You have a summary statistic of this observation. And then you look how closely these two summary statistics are to one another, okay? So you basically compute some kind of distance between the two. And if the distance is small enough, smaller than epsilon, then you keep that parameter value that led to this observation X, which is close enough to your observation. Okay, and then you repeat that for many, many, many values of the parameters that you draw from your prior. And then eventually what you can show with this simple algorithm is as epsilon goes to 0, and assuming that your summary statistic is sufficient, then indeed the sampling distribution that you will have at the end of the day correspond to the posterior distribution P of theta given X naught. Okay, so very simple algorithm, but it has quite a few issues. The first one is, how do you choose the summary statistic? How do you choose in particular a good summary statistic? How do you set epsilon? How do you set this distance? What if you are not only interested in sample from the posteriors, but on actual density for the posterior? And what if you don't have just one, but maybe several observations? If, for example, you get a second observation X naught, then you would have to run the thing again and again and again. Okay, so this is not so convenient. So an alternative algorithm which we proposed a few years ago is called Neuralgia Estimation, or NRE, and it starts from the Bayes rule. So if you take the Bayes rule, which says that the posterior P of theta given X is equal to the ratio between the likelihood P of X given theta times the prior over the model evidence Px, what you can do is to rewrite this, or to factorize it into two terms, into two factors. First, the prior that you have, and by the way, that you can evaluate quickly. And another factor, which we call the likelihood to evidence ratio, R of X given theta, which correspond to this quantity, P of the likelihood over the model evidence. And the idea is to say that this quantity R, I will approximate it with machine learning. Okay. And actually, you can do so even in the case where you cannot evaluate the likelihood nor the model evidence. If the only thing you can do is to sample from the likelihood function and the prior, then that's sufficient. Okay. So how can we do that? Well, this is based on what is known as the likelihood ratio trick. And the idea is to basically rephrase that problem of estimating this ratio as a binary classification problem. Solving binary classification problem is something that we can do very well these days in machine learning and in deep learning. You can just instantiate any kind of neural network architecture, you feed in the data, you train on the constant pre-loss, and then you're done. Okay. But how do we go from this problem, which aims at estimating the ratio, to a binary classification problem? Well, the trick is to create an artificial data set that would be made of two classes of data. In the first class, what you would do is that you draw random pairs from the joint distribution P of X and theta. Okay, so you would, for example, very concretely, you draw parameters from your prior, and then for this parameter theta, you produce a synthetic realization by running forward your simulator for this particular value of the parameters, and the two together, theta and X, would correspond to a random draw from this joint distribution. Okay, so you would repeat that many, many times, and you would label all these pairs, let's say, with class 0. Then you would do the same. You would consider the second class, which would correspond to pairs that are drawn from the product of the marginals, Px and P of theta. Okay. And again, this is something that you can do easily. So to generate thetas, you just draw from your prior, and to generate X values, which are not tied to theta, what you would do is that you draw another theta from the prior, okay, which is not related to the theta that you've drawn before. Okay, you do it independently, and then for this independent theta value, you produce a realization X, and then together this X with the first original theta correspond to a pair which is drawn from this product of the margins. Okay, then you repeat that again. You produce samples for the second class. Okay, so you can do so, for example, a few million times, and then you train a classifier that will take as input a pair X and theta, and the job of this classifier will be to tell if this pair comes from the joint or the product of the margins. Okay. So if you did your job well, then you should obtain a classifier which is close to the Bayes optimal classifier and which correspond to this quantity. So the Bayes optimal classifier would be a function which takes as input some pair X and theta and then produces as output the ratio between the likelihood of over the joint distribution over the density of the joint plus the density of the product of the margins. Okay. And so this is nice because we can then massage the output of this classifier to come back to the likelihood to evidence ratio. Okay. If you do D over 1 minus D, okay, what you get is the ratio of the joint over the product of the marginals. Okay, the joint itself can be factorized as P of theta times the likelihood. Okay, then you would have the two priors that cancel, and then you are back to the likelihood to evidence ratio that you wanted to approximate in the first place. Okay, and once you have that, okay, then you can move on and do inference. Okay, so if we have to summarize how we could do inference with neural ratio estimation, first you run your simulator, you produce this data set, okay, these pairs of theta and x. Then you train a neural network, which takes as inputs both the parameters and the observables x, okay? And you train it as a binary classifier over, for example, the cross-entropy loss. So you minimize the cross-entropy loss. And then you you massage the output of the classifier to produce the ratio, an estimation of the ratio. Okay, and once you have a good estimation of the ratio, then you would, for example, multiply it with the prior distribution that you know, and then you would obtain the corresponding posterior distribution for the parameters and the output. Okay. The nice thing with this algorithm is that it's amortized, meaning that you don't have to repeat the training for any new observation x naught. Okay, the only thing that it's as fast as just doing a forward pass through the network. Okay, the only thing that you would do is that you would change the input here for the neural network, and then you would evaluate at any value of theta that you are interested in, and each evaluation together with the prior would correspond to an evaluation of the posterior density. Okay, from which you can then, for example, draw these contours or these credible intervals. Okay. Okay, so this is the first part of the talk. This was just to show you how this works. Now we'll go over a few applications that I've been working on. So I've been mostly applying these algorithms in physics, in astrophysics. I will go first over a case in particle physics in which physicists, what they do is that they simulate the collision. So this is a simulation of one of the experiments at CERN, at the LHC. And what they do is that they collide two beams of protons at very high energy, and then they simulate what would be the outcome of these collisions and what they expect to observe in the detector that they build around the point of impact. Okay. And okay, and what they do then want to do is to do inference, for example, on the model, on the parameters of the standard model, like for example, to infer the mass of the Higgs boson. So this is something that you can do with this kind of algorithm because everything can be simulated forward, and therefore you can build a data set that you need to do neural ratio estimation, for example. And so this is what we did in one of our first applications. And if you compare to the historical analysis, which was done, for example, using histograms, as I mentioned earlier, you would get, for example, an error on the likelihood ratio quantity, which would be this orange line. And you see that using machine learning algorithms like the one I've presented, so the one I've presented, NRE is in this plot called Carl, but this is the curve that you see in green. All the other curves are improvements that you can achieve by just using more stuff from the inside of the simulator. But you see that eventually you reach an error which is below the error that you would get with traditional approaches. Okay. Concretely, from a scientific point of view, it also means that the contours that you get are usually more constrained because more accurate. And this is what you see on the figure on the right. If you compare the contours, the constraints that you can put, for example, on parameters, with respect to the traditional methods in orange. When you do the same but using a better inference algorithm, which is more accurate, then you get the other curves, for example, the red or the blue ones. Okay. Another case that we studied is in the case of dark matter substructures. So this is an example from cosmology or astrophysics, and which is interested in the study of dark matter, and in particular in trying to measure the mass of the dark matter particle. And so depending on the mass of the dark matter particle, what we should see in the universe can change drastically. So there are two main hypotheses this day. Either we have a so-called cold dark matter model, which happens where the mass of the dark matter particle is quite large, so meaning that these particles are heavy, and if they are heavy, they will tend to clump together because of the gravitational forces. And these clumps of dark matter should have an effect on what we observed in the sky. Okay, and on the other hand, if the mass of the dark matter particle is very low, then that should correspond to the case of the warm dark matter model, in which dark matter particles should be diffused more or less evenly across the universe. Okay, so which one of these two theories should we believe, or which one of the two theories is the most plausible given the data that we have, given what we see in the sky? This is one of the big questions that astrophysicists are trying to answer. So how can we answer this, since dark matter is not visible? Okay, this is a synthetic image in which all these points would correspond to clumps of dark matter, but we cannot see it in the sky. Okay, what we can maybe see is indirect effect of these clumps of dark matter, and one of these effects can be maybe observed in what we call gravitational lenses. So this is a diagram which corresponds to a gravitational lens. So you have to imagine that you have some observer like us on Earth, okay, and we want to observe some galaxy very far away in the cosmos. But in the middle, between the galaxy and Earth, there is a massive object, like, I don't know, a black hole or another galaxy. And if this object, which is in between, is very heavy, what will happen is that it will distort space-time, and the light which is emitted from the object behind can still be reached, even though it should be occluded by the object which is in the middle. Okay. And if this happens, then this is the kind of image that you should observe. And this is indeed an image that you observe. This is called an Einstein ring, in which what you see in the middle is this object, which is the obstacle. But you see this ring, which is actually light, which is emitted from an object which is behind the object in the middle. Okay, so for example, this could be a galaxy, that galaxy which is there, okay, but which you do not directly observe. You only observe the distortion of the lights around the object in the middle. Okay, so why is this interesting for astronomers or astrophysicists? Is because if, in addition to that, there are clumps of dark matter, okay, like the small dots that you see there, they should have an effect, a gravitational effect, on the light which is going on there, and also on the kind of lenses. So it should distort, maybe in very subtle way, but it should also distort the kind of lenses that you observe in the sky. Okay. And so this is something that you can simulate, and this is what we did for synthetic data. We have been simulating gravitational lenses that were perturbed by population of dark matter subhalos, okay? And then when you do inference on these parameters that control, for example, the mass of the dark matter particle or the distribution of these subhalos, then they should have an effect on the images, the synthetic realization that you observe, and then if you should then be able to use them to do inference precisely on these parameters, okay? So this is what you see there. we've been using neural ratio estimation on pairs of parameters and images, okay? And then we train a neural network to approximate the ratio, then we're combining with the prior, and then we get an estimate, an approximation of the posterior distribution. And this is what you see there on the right figure, okay? And here what we do is that we condition on more and more and more observations. And as you get more and more observations of the same phenomenon, you can then constrain more and more the parameters that you're interested in. And again, this is a case where we don't have a direct access to the likelihood function. Still, we can go around it using, for example, simulation-based inference. Okay, a third example, again from astronomy, and again related to dark matter. So this is another secondary effect, I would say, of the dark matter particle, or of these clumps that I was talking about. So if you look at the Milky Way, our own galaxy, what we observe is that, okay, there is all these stars, including our sun, but there are also what we call streams of stars, like the one that you see here, which is called the GD1 stream, which is really a very long stream of many, many stars. It's really elongated in this way and goes around the Milky Way. There is another one, which is called Palomar 5, which is another stream of stars. But what is really interesting to see or to observe is that when you look at the density of the stars on these streams, then we observe that there is a gap. Okay, there is really like a hole in the stream. And scientists, astrophysicists are wondering why. And one of the reasons is that dark matter exists. It exists as a particle, which is heavy, possibly heavy, so that it groups together into clumps. And these clumps may then gravitationally interact with the streams, such that some of the stars that were there were basically kicked out at some point a long time ago. And that would explain the kind of gap that we see in the GD1 stream. Okay, so this is a simulation of this, where you would have a stream which is not perturbed, and then a stream which is perturbed by two subhalos. And you see that if there is a perturbation there, then that may explain the kind of decrease that we see in the densities and disposition. Okay, so again, we can simulate that. We can simulate what would happen if dark matter has this value for its mass, and what is the expected density that we would observe. Okay, and then we could produce these pairs x and theta. Okay, we could feed that all the way down to a neural network to approximate the likelihood ratio, and then to use it at the end of the day to do Bayesian posterior inference on the mass of the dark matter particle. Okay. And here what we see is that when you do that, at least on the synthetic data that we, or rather for the model that we've considered, then when you do inference on GD1, so the actual and only observation that we have, then this observation, and for the model that we consider, would suggest that the dark matter particle has a mass which is at least above 10 in this case, which basically exclude this, or would give, let's say, rather a stronger preference toward this cold dark matter model over the warm dark matter model. Okay. So this is another example. Okay, so these were 3 examples from Astro. What I like about these examples is that when you discuss with physicists about this result, they are usually very skeptical. Okay, and they may not believe your algorithms, they may not believe your neural network, and they may not believe the output which is produced by this surrogate. All these approximations that we are doing, are they really reliable? Can we trust them to the point that we should really discard a whole family of scientific theories over another one? Okay, because this is basically what's the consequence of this single plot. If you really believe that this result is correct, then there are dozens of papers that you can throw to the bin because they do not agree, they are not plausible with the data that we have. Okay, but for that you really have to make sure your inference procedure is correct and that your results are at least not too wrong. Okay, so there are several ways you can use. One of them, which I like, is called coverage. And it's basically something that you can use, not to check that your results are correct, but at least to maybe spot when your model is not correct. Okay, so it's a necessary, I would say, condition for correctness, but it's not sufficient. And the idea goes like this. So you would compute pairs x and theta from the join that you would put in a validation set. Okay. Then for each of them, you would compute the approximate posterior p hat of theta given x. Okay. So you would just use the observation, the synthetic observation x, and you would compute the approximate posterior that you get with the procedure. And then from this approximate posterior, you would compute, let's say, the 1 minus alpha credible interval. Okay. And you would look if theta, the parameter which is associated with x, falls inside this credible interval. If your credible intervals, I would say, are well calibrated, what should happen is that they should be inside this 1 minus alpha credible intervals with a proportion which is exactly 1 minus theta, 1 minus alpha. Okay. So if you compute the actual fraction of sample for which theta is contained within the interval, and you call that the empirical coverage probability, then we should, ideally what we should have is that the empirical coverage probability is exactly equal to the nominal coverage probability, and that should happen for all levels alpha that you consider. Okay. So this is an image that I pictured, which I took from a paper which does this kind of test or diagnostic for statistical coverage. And so basically the x-axis corresponds to the alpha, the confidence level, the size of the credible interval. And then the y-axis corresponds to the empirical coverage. And if your procedure would be exact, then the empirical contours or empirical credible interval that you compute should be just that this curve is exactly sitting on the diagonal. In that case, you would be perfect. If you see that the curve is above the diagonal, that means you are making some mistakes, but actually it's fine because it means that your approximate contours are just a bit, or maybe significantly more, but they are larger than what they should be. Okay, meaning that on average you would be more conservative, so you will restrict less the parameters than what you could have achieved if you were sitting exactly on the diagonal. If the curve was below the diagonal, then you would have problems because you would be your procedure would be overconfident, meaning that the approximate contours that you compute on average would be smaller than what they should have been. Okay, and this is where there is some kind of danger, because for example, if you take back this result, okay, if the posterior probability, if our approximate posterior probability would be such that, okay, we would have moved everything to the right with very high confidence, then very likely in this case we would be overconfident, and we would exclude many theoretical models because of these wrong predictions. On the other hand, if the procedure is conservative on average, that means maybe the true contours or the true posterior density would have been there, okay, but okay, we are just being a bit more cautious than what we could have been, and in this case, you see that the posterior is okay, would have been a bit to the left, meaning that we exclude fewer parameter values. Okay. Okay, so this is something that you should do. I think if you use SBI and you have the computational budget to produce these plots, then this is really something that you should do to really be able to trust and use the kind of inference result that you get out of these algorithms. Unfortunately, this is what we have shown in a recent paper. If you look at current algorithms from simulation-based inference, so neural ratio estimation, which I've been talking about, but also neural posterior estimation, or SNL, which tries to directly approximate the likelihood function, or even ABC, okay, what we've discovered is that if you take these methods and if you evaluate them on a bunch of benchmarks, so in this case, we evaluated them on 7 benchmark problems, and you compute these empirical coverage curves, then unfortunately, what we see is that none of the algorithms produce curves that are always above the diagonal. Okay, there are cases, for example, if you take an NRE, where sometimes the curve is below, sometimes it's above. The same for SNPE, the same for SNL, which is in this case for this benchmark problem always overconfident. It's the same there. It's, for example, for ABC, it's very overconfident for this problem about epidemiology, and so on and so forth. Okay, so there is no single algorithm that would be always conservative, always above the diagonal. This is what we've discovered, and this is true also for many computational budgets. So the number of pairs that you use to train these models, you see that regardless of whether you use 1,000 samples or a few thousands of them, you may still have this issue. Okay. So this is bad. I think it's it calls for caution, meaning that if you use simulation-based inference algorithm, and when I say that, it actually includes all inference algorithm or all approximate Bayesian inference algorithms. So the ones I've presented today, including ABC, but you could also do the same kind of curves for MCMC, and I'm quite sure you would see the same kind of results. So what I want to say with this is that, okay, these methods, they work very well. They've achieved very good results, and they allow to work on problems that we couldn't work on before. But you should still think about what you get out of these boxes. Okay, and one thing that you should do is really to diagnose the kind of result that you have, for example, by using these coverage curves. Okay, so another title for the talk of today could have been Averting Crisis in Simulation-Based Inference. This is the title of the paper that shows these empirical results, in which basically we advocate, of course, for SBI methods. We really believe they are useful and allow to work on problems we couldn't before, but we should be cautious in how we use them. Okay, otherwise it may lead to basically wrong scientific results. Let's say you would be in a regime where you are overconfident, then you would basically exclude entire scientific theories which you should not have excluded. Okay, not because they are wrong, but because your approximate procedure is wrong. Okay. So to summarize, and that would be the end of my talk, I would say that much of modern science is based on simulators, and that's very useful to make precise predictions, but at the same time, it makes inference quite challenging. However, machine learning enables powerful inference methods of the kinds I've presented today, and they work across many problems from the smallest to the largest scales. And I really believe that advances in simulation-based inference will really translate in scientific progress. However, before that happens, I think future work is really needed to make these methods more robust and more reliable from a scientific point of view. And that's it for me.
Thank you so much for the presentation, Gilles. Now, if you have some time for questions,
Sure.
So either you can write them on the chat and I'll read them out loud for you, or you can ask them yourself. Just raise your hand. Yeah, Sivo?
Yeah, thank you, Joe, for the nice presentation. So I have a question more on the practical side. So I was wondering how your this ABC framework can be sensitive to the knowledge or the quality of of our knowledge about the prior distribution. So since we're working with something quite similar for dynamical systems, we like to calibrate these parameters based on observed images or observed quantities, so like these kind of inverse problems. But we don't have a very good knowledge about the prior. So what we have is only like several samples from the literature, for example. So what we do, for example, what I can imagine that we can do with this framework is to use something quite naive to say, okay, we set the mean, the max, maybe use a uniform LOR or use a Gaussian distribution to approximate that. So I'm wondering if you have any comment or insight on that. If we work with a poor knowledge with the prior, will that lead to, so I mean, how damaged that can be?
But I wouldn't talk about damage. Because, I mean, Bayesian inference, what it does for you is that you start with some prior beliefs about the model parameters. So if you don't have any prior beliefs or any strong belief, then that's fine. Okay, you could just say that you don't know anything or barely anything, and you would set uninformative priors like uniforms, and that would be fine. Because then you would then refine. You would then use the Bayesian procedure to refine your beliefs, to update your beliefs with your observation. Okay, and then you get, after updating your beliefs with the observation, you get a posterior, which is now like some better informed or educated version of your prior. Okay. The thing is that if you repeat this over and over, at some point you should, I mean, you have learned something along the way, and so you should not do as if you didn't know anything. At some point, you should integrate more and more this knowledge that you have about good parameter values directly into the prior. But of course, so I mean, when you do Bayesian posterior inference, the priors matters a lot. And that's something that should, I mean, you should spend some time just specifying priors that make sense for your scientific problem. Because I'm quite sure there are plenty of ranges of values that do not make sense, or you are very confident you should not use them, and that's something you should basically encode in your prior beliefs.
Thanks, I see your point.
Thank you, Sivo. Any other questions? Well, I can ask a question. In terms of generating data, in your opinion, what do we like? What should we aim for in terms of like, does the data need to be more general? Does it need to be like able to generalize the real data to copy the training data, or the fidelity, or how diverse will it be? Because I guess it will struggle with like creating something that's out of the distribution.
Yeah, so when you use these algorithms, usually you assume that your simulator is well specified, meaning that there is really some configuration of the parameter that could have led to what you actually get. Okay, if you know in advance that regardless of the parameter's value that you will set, you will never be able to reproduce what you see. Okay, then that means you are in a case where, in a regime where your simulator is misspecified. Okay, you could still do inference, but that will lead to plenty of problems. I think in this case, you should just spend time and trying to improve first your scientific model, your simulator. And one way which is done, for example, often in physics, is that, okay, maybe you have a good vision of the actual process that you're interested in, but maybe there are plenty of sources of noises that will happen because of, I don't know, the instruments and things like this, that will mess with the actual, or that will produce not exactly the kind of data that you would expect from the noiseless version of the simulator. but that you should integrate nevertheless because they are part of the data generating story that you are trying to tell to yourself about how this data that you get has been generated, okay? And so you can do so by, for example, extending your scientific model with nuisance parameters that would basically expand the space of possible observations with all the things that you know that you don't know, basically. All these sources of noises, for example, that, okay, you know they are there, but you will not directly measure them, but at least you account for them and you anticipate for the fact that they are there. And depending on their own configurations, they may lead to this or that observation. So that's something you can do with, for example, nuisance parameters. But
right.
if you really start with a model which is poorly specified, and there is no chance you will even get close to a real observation, I think you are not yet ready to do inference.
Okay, thank you. And yeah, I think I can ask another question. In terms of like, how do you see the future from like 2022 and like, I don't know, from here to 2030? Are we going to use a lot more of augmented data and generated data to solve problems? What are your views on that?
But I think scientific simulators are getting more and more accurate. I think that's a fact. But when it comes to inference, usually we make sacrifices. We consider very gross approximations of these things that we know we can simulate. And we never do, or almost never do inference with the, I mean, let's say you had the freedom to write the most precise kind of scientific simulations, regardless of how long it would take just to produce one observation. If you could do that, then I'm quite sure you would not use the kind of simulator that you assume today when you do inference. But here in this setting, I think we are close to that. You have the freedom to write very complicated simulations. And at the same time, we start having tools that enables at the same time to do inference in these very high fidelity simulations. So I think, of course, there is still progress depending on the kind of scientific simulator that you use. So I don't know, for example, if you were to simulate weather or climate along a very long time horizon with a very, very high resolution, that's something you could do. That would take ages to compute. But if you could do it, and if you could say, I want to do inference under this model, I'm quite sure you would like to do it. The question is how, and I think that's what we try to solve here with these new methods.
Okay, yeah, that makes sense. Thank you, Gilles. Any other questions?
Actually, I don't have a question, but yeah, just to follow up on this, I think that it will be probably, it's still not completely a hot topic now, but this point of generating the data will be like exploding. So I see you are one of the few groups working on that. There are not so many people working on that, but I see your point, and I completely agree on what you're saying. I think that this will help a lot, of course, from the scientific point of view, but also saving lots of money for the generation of some data, no?
Yes, but actually, I think that's really dependent on the scientific field that you're in. So when I was at CERN, on working on collider experiments, high energy physics, actually more than half, I don't know if that's something you know, but more than half, so they have their own data center, I mean, several buildings full of computers, and more than half of the computational budget, you know what it is for? It's just to simulate data. They just run their scientific simulation forward to produce synthetic realizations. They just do that all day long. And the goal is really to start with their most precise description of nature, in a sense, to be as close to that, and then to make use of this data to then do inference and reason about the observations that they do get in their experiments. So I hope that's something that will propagate across other fields of sciences, but I think that will happen if these techniques become also maybe easier and easier to use.
Yeah, more towards the fundamental science, so that it can be used in cross-discipline. Yeah, super interesting. But what is your point about the generation of synthetic data for design experiments?
Yeah, so I think that's very interesting, but that's another direction that we could have talked about. Because so when it comes to experiments, you may wonder what is the best, let's say, what is the best experiment that you should carry out to get the most of the observation that you hope you will collect and that you will be able to use to reason about your theoretical model. And so again, if you can simulate the experiment itself, and if that experiment comes with their own set of parameters, then you can do optimization on this experiment. And so that's a whole field in itself, which is called experimental design or optimal experimental design, and that you can use to basically simulate what would be, let's say, the information gain that you would get if you were to run this experiment. And then you can do optimization in this space of our experiments to try to identify which is the one that would lead in expectation to the, I don't know, the largest increase in certainty about some parameters of interest. So that's something you could do, but I mean, it's doing this thing, but inside a for loop over realization of the experiment. So that's very computationally heavy. Even though we know you can express this kind of problems, I think we are still quite far away from doing that in practice.
Yeah, I know, but it's like, yeah, I really wanted to see your point about that, because it's, I think it may be something very promising in terms of real-world applications. So.
Yeah.
Okay, thank you.
Thank you.
So before we leave, sorry if I'm copying something in the chat box. So we have, and this is also, of course, for you, but we will send you an email about that. So we have every year, now is the 4th edition, we are organizing a workshop as part of the top conference in computational science, the International Conference on Computational Science. We are organizing a workshop on machine learning and data simulation for dynamical systems. So this year we have the deadline the 18th of February. This year it will be in London, fingers crossed in person this time. And yeah, as I'm saying every week now, you're very welcome to submit an abstract or a paper. If you submit a paper, it will be published on Lecture Note in Computer Science. And as this is a top conference, it's still, you know, let's say, good point in the CV, especially if you are an early career researcher. So that's it for Gilles. To you, Cesar will send you now the link to the workshop to invite you in case you are happy to be part of that, and also other links to special issues that we have. This is also for everybody else which is still online, even if you are running late. So thanks for attending. Cesar.
Thank you. Thanks again for the invitation.
Yeah, thank you so much for your talk. Very interesting, very relevant as well.
Yeah. Thank you very much.
I was trying to look at the link that you posted, but it does not work.
Oh, let me see if it's not working. I will send that again in the chat box. So the link is this one. So
I can send you a follow-up email with the link.
Okay.
Yeah, absolutely. But the link is here, so in case also for the other, because
yeah,
it would.
Perfect. Yeah, that works.
Yep.
Okay.
I think. Well, thank you everyone. Thank you, Gilles, for doing this, and yeah, see you soon.
Thank you. Bye bye.
Thank you, Gilles. Bye.